Dear children, today we'll discuss about a very important topic of this chapter, current electricity. The topic is potentiometer. What is potentiometer? You remember, it is a device used to measure the EMF of a cell, the internal resistance of a cell, and to compare the EMFs of two cells. Now come to the principle of potentiometer. What is principle of potentiometer? You remember, when a constant current flows through a wire of uniform cross section, then potential drop across any part of the wire is directly proportional to the length of that part of the wire. Repeating again, when constant current flows through a wire of uniform cross section, then the potential drop across any part of the wire is directly proportional to the length of that part of the wire. Let us prove the principle. We know V is equal to IR, that is your Ohm's law. This R is your rho L by A. Rho is specific resistance of the wire, A is area cross section of the wire, L is length of the wire. This equal to I rho by A into L. This bracketed term is a constant. Why? Already told, constant current means I is constant. Uniform cross section of the wire means A is constant. Rho specific resistance or resistivity, that is constant for a wire. So the bracketed term is a constant. You can write it as K, KL. As K is constant, so you can write V directly proportional to L. This proves your principle of potentiometer. This K you can write V by L. This equal to I rho by A, as it is potential drop per unit length, so it is called as potential gradient of the wire. Now come to the construction of potentiometer. You see the figure, it consists of 4 to 10 meter long constant time or manganese wire. You know, constantan and manganese, they are the alloys. They have high resistivity and low temperature coefficient of resistivity. Instead of taking this 4 or 10 meter long wire direct straight, we are taking several 1 meter long wires, because if you generally in our laboratory we are using 10 meter long potentiometer. If you take 10 meter direct straight, it is very long. That means the laboratory may not accommodate this long potentiometer if you take this 10 meter direct straight. So what we are doing here, several 1 meter long wire connected together by means of thick copper strips. These are copper strips, and these wires fitted on a wooden board parallel to a meter scale. You see, it is the meter scale, 0 centimeter to 100 centimeter. Here we have taken 4 meter long potentiometer. The two ends of the wire, you see, they are connected to a battery and a rheostat through a key. When you close the key, then current flows through the wire. As it is positive terminal, so current will flow like this. This circuit is called as driving circuit, as it drives current, or auxiliary circuit, or you can say it is primary circuit. And you see, this part is your secondary circuit. Secondary circuit. In this secondary circuit, you have a cell connected to a galvanometer, resistance box, and a jockey. It is all about your construction. So, what is construction? It consists of 4 to 10 meter long constant or manganese wire. These wires are of high resistivity and low temperature coefficient of resistivity. Instead of taking 10 meter, or instead of taking the wire straight, we are taking several 1 meter long wires connected side by side by means of thick copper strips parallel to a meter scale on a wooden board. The two ends of the potentiometer wire are connected to a battery and a rheostat through a key K. When the key is closed, then current flows through the circuit. This is called as driving circuit or auxiliary circuit. And in the secondary circuit, we have a cell connected to a galvanometer, resistance box, and jockey. And you remember, this secondary circuit can be changed according to your requirement. Now come to working. Here we have two cases. In first case, we have to compare the EMFs of two cells. What will you do? For your convenience, you take the wire straight. I am erasing this. I have taken the potentiometer wire straight. Just I am assuming. Across this potentiometer wire, you have a battery and a rheostat. It is a key. You will mark this box at the end of the potentiometer wire because it is your Constantan or manganese wire, but this wire is the connecting wires, means no potential drop along this wire. These are of very good conductor. It is your auxiliary circuit. In the secondary circuit, you have two cells like this. Let it be EMF E1. This cell has EMF E2. You will connect a two-way key to a galvanometer, then a resistance box, then to a jockey. Now, first one, to compare the EMFs of two cells. When the key is closed, then current flows like this. Now, let this key is K1, this key is K2. Now you close this key and open this key, keeping key K1 closed and K2 open. When you close this key and open this key, then what happens? The cell E1 is connected to the circuit, and you move the jockey along the wire. Suppose the null point is obtained at here. Let this length is L1. That means the jockey J is moved till null point is obtained. Let L1 is equal to balancing length. L1 is equal to balancing length. Therefore, E1 will be small k L1. What is small k? That is potential gradient. Then, why E1 is equal to k L1? Now you can apply Kirchhoff's second law, that is Kirchhoff's voltage law. Now you see, you take this closed circuit. At here, this length you have taken L1. The null point is obtained at here. Null point is obtained means no current flows through the galvanometer. If no current flows through the galvanometer means current here 0, here current 0, here current 0, up to here current 0. Similarly, here current 0. In this part means from this to this, the current is 0. But in this part, from A to B, the current is flowing. Why the current is flowing? That is due to this driving circuit. So now you can say when no current is drawn from this cell, then the potential difference across this cell is called as EMF. Now you apply Kirchhoff's second law. When you go like this, you take this closed loop. From this to this, there is no potential drop because it is the connecting wire. From this to this, it is E1, no current is flowing. From this to this potential is lower because you see current is flowing like this. This potential is lower, this potential is higher, so it is negative. Minus V is equal to 0. What is this? This potential drop V is equal to, or E1 is equal to V, as V is equal to KL, means L here we have taken L1, so E1 is equal to KL1. In the same way, now you open key K1 and close key K2. Then what happens? E1 is now out of the circuit. Now E2, the second cell, is connected to this circuit. Keeping key K2 closed and K1 open. The jockey J is moved till null point is obtained. Let L2 is balancing length. Let L2 is equal to balancing length. In the same way, you can explain that E2 is equal to KL2. It is your equation number 2. So here you can put question, the K value that remains same. The answer is yes. Because in the null point, the potential gradient along the wire doesn't depend upon the secondary circuit. Because when no current flows to the galvanometer, that means these cells do not send any current. The potential drop along this wire, that is due to only this cell. That is only due to the driving cell or the auxiliary cell. So you remember, when galvanometer shows no deflection, or in the null point, the potential gradient along the potentiometer wire doesn't depend upon the secondary cells. Now E1 by E2, that is KL1 by KL2, that is L1 by L2. Here we got the relation E1 by E2 is equal to L1 by L2. Here we have compared the EMFs of two cells. The L1 and L2 length we can determine from the scale. So now come to the second application, that is to determine the internal resistance of the cell. To determine internal resistance of a cell. The auxiliary circuit that remains same, only we have to change the secondary circuit. Here it is the resistance box connected parallel to the secondary cell. It is the key. You name this key as K1 and it is K2. Here it is galvanometer. Here it is resistance box. And it is the jockey. First one, keeping K2 open. The jockey is moved till null point is obtained. Let L1 is equal to balancing length. You see here, when K2 is open, then this resistance box is out of the circuit. Only the cell is connected to the circuit. As discussed earlier, that this EMF E will be KL1. Equation 1. Now, you close this key. Now, keeping K2 closed, the jockey is moved till null point is obtained. When it is closed, then you see here the resistance box is connected to the circuit. Here one closed circuit you are finding. When it is open, the null point, no current flows to the or no current run from the cell. But when it is closed, as resistance box is connected across the cell or the circuit is closed, some current is flowing in this closed loop. As the current is drawn from the cell, now the potential drop across the cell or potential difference across the cell is not the EMF, that is the terminal potential difference. Now you take this null point will shift support to this one. Now you consider L2 is equal to balancing length. Therefore, V is equal to KL2. Why V is equal to KL2? Because as current is flowing this loop, so potential difference across this cell is not the EMF, that is the terminal potential difference. Now, you divide these two equations. E by V is equal to L1 by L2. You consider the internal resistance of the cell is smaller. E you know, that is I into capital R plus small r. What is capital R? Resistance provided in resistance box by this resistance box, and this V is equal to IR. It is your terminal potential difference. You know terminal potential difference is current into external resistance. It is your equation number 3. From equation 3, I into R plus R by IR L1 by L2 or R plus R by R, that is L1 by L2, or 1 plus R by R, that is L1 by L2, or R by R, L1 by L2 minus 1, that is L1 minus L2 by L2, or smaller L1 minus L2 by L2 into capital R. L1 and L2 you can determine from this scale, and capital R, that is resistance provided in the resistance box. By putting these values, you can find what is the internal resistance. And this completes your potentiometer topic. What is sensitivity of potentiometer? You just remember, sensitivity of potentiometer, sensitivity of potentiometer is more when potential gradient is less. Potential gradient you know V by L. That's why we are taking the potentiometer wire of more length, that is 10 meter long. And also you can increase the sensitivity. You know K is equal to I rho by A by decreasing current in the auxiliary circuit. By decreasing current in the auxiliary circuit means by increasing resistance in the auxiliary circuit. This completes your chapter number 3.